Hey guys, this is my lab 4 on oscillations. The purposes of this lab, in terms of option 1, was that we had a video of a point mass on the end of a spring, which was attached to a fixed end. It then oscillated in both the x and y directions. Using Tracker, we were able to extract the observational x and y coordinates, and then using GlowScript, we were able to make our own experimental model, to which we could then compare the x and y position time graphs of the experimental and observational model. Along with that, we also just made a total energy graph for the entire system in the experiment. Overall, the experiment was very interesting. However, due to my own coding error, I could not get the experimental to match the observational model. So the principles we used in this was we used Newton's second law, which is the momentum principle, because we are trying to find the updated position as a function of time. So thus, we have to use the updated velocity to then get the updated position. Along with that, we are also using the energy principle. However, since all of our system is inside the system, then we don't have any surrounding work, and since it's the same temperature, we don't have any thermal energy. Thus, we can set the energy of the system equal to 0, and then we can figure out, obviously, the potential and kinetic energy within the system that are in equilibrium to make it 0. And then these are just the equations for the potential energy and kinetic energy listed here. So like I said before, we have a mass attached to a spring at a fixed point, and the system in this, since we're putting everything within the system, would be the Earth, the spring, and the mass, as those are the objects exerting the force on the mass. And then in surroundings, like I said before, we have none. So for initial conditions, we had the mass of the ball, which was extracted from the pre-lecture video. The initial position, which is extracted from Tracker. The initial velocity is 0, but then we already know the gravitational constant. Spring constant we got from the pre-lecture video as well, and along with the relaxed length, we got it from the lecture video as well. So in terms of the coding, there wasn't much change other than just, putting in like the correct equations for all the different stuff. So obviously the L vector had to be changed, L hat had to be changed, and S had to be changed. We had to change our kinetic energy, potential of gravity, potential energy of the spring, and our total energy, obviously, to match their equations. And then within the calculation loop, we obviously had to update the F-grav vector, update the F-spring and F-net, and then use our updated velocity and position functions. And then the rest is kind of just redoing these where you're inputting the equation for the right force. So the results, as you can see, are on the right. So we have the total energy graph, the x position versus time graph, and the y position versus time graph. So the energy graph actually turned out exactly how we expected it. As you can see, the potential energy and kinetic energy fluctuate in terms of when the spring's in motion and whether it's in motion or about to be in motion. But as you can see, the total energy of the system stays constantly at 0, which does show that the system is in equilibrium. And there's really no fault with this graph that I can see as of now. On the other hand, in terms of the position graphs, this was a little different. The experimental model did work well and was calibrated correctly. So we can see that it fluctuates between 0.64 meters and negative 0.67 meters. And it goes back and forth. And then same with the x direction, it fluctuates back and forth between about 0.1 to 0.2 meters. However, the model, I don't know if it was a scaling part of the code or a difference in the equation, but it shows fluctuation. It's not as high. It shows very little fluctuation. I really have no explanation for this other than, it's just being an error within my coding. So those are the sources of error that I found within my own experiment. And then the discussion, did the system follow the energy principle, which, as I stated before, yes, it followed it, because you can see that it's satisfied, as if the total energy is 0, then we can see that the total energy stayed 0 throughout, and thus the energy principle was satisfied. And then with the second part, we were just trying to estimate the period of oscillation in the x position and y position. So if you actually go back to the graphs and you just take the average of the time between the crest of the troughs is one oscillation. So using that and estimating it, then we can get x oscillations is like 1.67 and y's is 1.3. Since we know that the oscillation of a spring is equal to this, then we can use these periods to solve for mass or the spring constant. And that is it.